Solving exponential equation 6.3. You need a graphing calculator, amongst other things. So determine the solution to an exponential equation using a variety of strategies. So one of which might be the graphing calculator, and one of which will be an algebraic solution. But the chessboard has 64 squares which alternate between two different colors. Interesting fable associated with the invention of the game of chess. The king was so pleased by this game, they let the inventor choose his payment. And the guy said, I want you to put 1 grain of rice on the first square, 2 grains on the second square, 4 grains on the third square, and so on, right? Doubling each time. And this pattern can be modeled by the exponential function, y equals a times b to the x minus 1. So you notice there's a little adjustment in the exponent, right? We don't say y equals a times b to the x, we're saying y equals a times b to the x minus 1, where x represents the number of the square. And the reason is we want to have 1 grain of rice on this first square, and then we want to double. So your a value is 1. That's your initial value, right? We're starting with 1 grain of rice. We're doubling, so we put a 2 there, but on that first square I don't want to double. So if I just put an x there, then I'd say on the first square, you go 2 to the 1 is 2, times 1 would give you 2 grains of rice. So what we're doing in effect is backing off the doubling period by 1 square, right? By doing this, y equals 1 initial times 2 to the x minus 1. So on which square of the chessboard will there be 128 grains of rice? So we would say, okay, so I need 128 is 1 times 2 to the x minus 1. And keep in mind, x is the number of the square, right? It's which square. So to solve this, we can basically kind of ignore the 1. Right? So we could just write, or you could say, well, I'm going to divide both sides by 1. So I get 128 is 2 to the power of x minus 1. Now, we might recognize 128 as a power of 2. So we use our fingers and we count it up, right? 2 to the 1 is 2, 4, 8, 16, 32, 64, 128, right? So 128 is 2 to the power of 7. So we could now say, okay, 2 to the 7th is 2 to the x minus 1. So what do we know about 7 and x minus 1? They must be, both got 2's here. So the 2's are the same, so 7 and x minus 1 must be the same, right? So at this point, since we have the same base, we can just equate the exponents, right? We could say 7 is equal to x minus 1, so what's x? 8. So the 8th square, right? So we have 1 grain here, 2, 4, 8, 16, 32, 64, 100, and we ran out of ink, 128. 128. Yeah, virtual ink disappeared. Okay, so on which square do we have 128 grains? On the 8th square. Okay, so let's clean this off. Let's clean this off. We need to go down a page. So determining and solving an exponential. So here's somebody's solution, right? Now you could graph this as well, right? We could graph y1 equals 1 times 2 to the x minus 1. We would graph y2 equals 128. We would set our window such that we could actually see that far, right, to get the 128. Or you can go into the table of values, right? So there's a couple of ways. You could do it graphically. You can look in the table of values. Elliot's solution, rewriting using each side with the same base. So that's the one we did, right? 128 is 2 to the 7th. So that's the solution that we showed. using a system of equations and graphing technology, right? And you can look through all of these different solutions, right? So we graph y1 as 128, y2 as the exponential, and we find the x-coordinate of the point of intersection. That'll be our solution. Okay, so that's in there as well. Right, so solving exponential equation when the bases are powers of one another. So this is what we want to do. If we can get the bases the same, and remember we practiced this the first day, right? Rewriting it as a power of 2 or as a power of 3. So if we can get the bases the same, then we can solve, right? As soon as the bases are the same, we get to equate the exponents. Okay, so we did exponent laws. So let's do this. 4 to the power of 3x minus 1 is equal to 128. So the first question, can I express 128 as a power of 4? So you go, well, 4 to the 1 is 4, 4 squared is 16, 4 cubed, and again, you can just sit with your calculator and go times 4. So 4 cubed is 64. 4 to the 4th is 256. So it won't work, right? I can't express 128 as a power of 4. But we know we can express it as a power of 2, right? Because we just did that. So what's 128? It's 2 to the power of 7. Now, what are we going to do with the 4? We're going to write it as a power of 2. So 4 is equal to what? 2 to the 2. But the 4 is raised to the exponent 3x minus 1. So we rewrite the 4 with the base of 2, we write it as 2 squared. Rewrite 128 with a base of 2, it's 2 to the 7. Using power to a power, what do we do with these exponents? So I get 2 to the power of what? 6x minus 2. Okay, let's do a little more detail. It's 2 to the power of 2 times 3x minus 1, right? We know we have to multiply. When we multiply, this is an expression. It's got to be put in brackets. So we have to use the distributive law, right? We have to distribute the 2 through there. So 2 to the 7th. So this is 2 to the 6x minus 2. Okay, so very important, when one of the powers is an expression, before you do any multiplying, you've got to make sure you put brackets around it. Okay? Otherwise, you get 6x minus 1. It'd just be wrong. Now, at this point, when we have the bases the same, what do we do with the exponents? We set them equal to each other. Right? If I say 2 to the this, right, we're really saying like 2 to the this is equal to 2 to the that. What can we say about this and that? They're the same. So we get the bases the same, we then equate the exponents, okay? We drop the bases, like who cares? Doesn't matter that it's a 2, right? We just drop the base, okay? You don't want to do that if you're playing baseball. Well, you shouldn't even have the base if you're playing baseball. You run around the bases. Okay, solve. So what's 6x equal to? 9. What's x equal to? 9 divided by 6. You will never leave that, right? You won't get 4 out of 4 leaving a fraction of 9 out of 6, right? It's 3 over 2.
Wait, what is it?
Now, you want to check this, right? Because you can. So take your calculator and go 4 to the power of, bracket, 3 times 3 divided by 2 minus 1. Put that in your calculator. What do you get? So hopefully, unsurprisingly, we get 128, right? So that's what you can check, right? So you're walking out of the quiz, you haven't bothered checking anything, and they're all wrong. It's just sort of like, yeah, come on, really? Like, you got time. Speaking of quizzes, let's do the quiz on Wednesday.
Woo!
Apparently that meets with approval. Okay, so it'll be Wednesday right after lunch in room 302. Okay, so Wednesday after lunch, 302, quiz. All right, let's do a bunch more. Okay, so first question, can we express 625 as a power of 5, right? Okay, and what is it? 5 to the... So you just try some different numbers. You go 5 cubed, nope, too small. You go 5 to the 4th. 5 to the 4th, right? Okay. So 5 to the x plus 1 is equal to 5 to the 4th. What's the next line? Bases are the same. What do we do with the exponents? Set them equal to each other. So what do we say? X plus 1 is 4. So what's x? Okay, 3 plus 1 is 4. You go 5 to the 4th. Hopefully you don't, because you already know the 5 to the 4th because you just finished doing that. Okay. So this one, I mean, since the 625 is a power of 5, there's not as much checking required, right? Like when you take a power of 4 and 128 and express them both as powers of 2, you want to do a little more checking there. Okay, so 8 to the 3x equals 16 to the 2x minus 1. So can 16 be expressed as a power of 8? No, it could be a multiple of 8, but that doesn't help us, right? It's got to be a power. So 16 could be 4 squared. Can we write 8 as a power of 4? No. So what's the common base for 8 and 16? 2. So what's 8 when it's written as a power of 2? 2 cubed, 2 to the 3, right? Okay, so this is 2 cubed to the power of 3x. What's 16 as a power of 2? 2 to the 4th. So 2 to the 4th to the 2x minus 1, right? Which I'm going to write in parentheses, right? Because we have to remember that we're now going to use power to a power. So what's on the left side? What's the expression on the left side? 2 to the power of 9x. Power to a power says you multiply. 3 times 3x, 2 to the 9x. What do we get over here? 2 to the 8x minus 4. Okay, so it's 4, and this time we put the 2x minus 1 in parentheses to remind us that we have to distribute the 4, so 4 times 2x minus 4 times 1. Okay, what's the next step?
Get rid of the 2's.
Get rid of the 2's, so what do we write?
9x equals 8x minus 4.
9x is 8x minus 4. Okay? Solve that. What do you get? Subtract 8x from 9x, you get x. So x is equal to negative 4. Okay? You want to check that? Go 8 to the power of negative 12. Right? Or go 8 to the power of bracket 3 times negative 4. Close bracket, hit enter. Get some value, right? Some decimal. Then you go 16 to the power of, right, which is your upside down v, bracket 2 times negative 4 minus 1. You hit enter. What do you expect to see on those two lines? The same thing. If you do, you got it right. If you don't, you got it wrong. Okay, and then you fix it. Because when you do your homework, remember, it's fix it, focus, practice, right? You try a question, you check the answer in the back. If it's wrong, you're going to look and see, what did I do? Where did I make my mistake? And fix it. If it's right, you carry on. Okay. No point in doing 12 of these questions, getting them all wrong. You're just going to teach yourself how to do it wrong very well. You'll be really good at getting the wrong answer. Generally not a skill that's highly appreciated anywhere, right? So, hey, I can get the wrong answer anytime. I don't even need to work at it. I can get the wrong answer. 6 to the power of 3x is equal to the square root of 216. What are we going to do with this? Well, first off, we can't have a radical sitting around, so we're going to have to change this. So we'll go with 6 to the 3x, just leave that. How do we write 216 as a power? Or sorry, square root of 216. What power gives us the square root? Half, right? So we go 216 to the power of 1/2. Now, can we write 216 as a power of 6?
I don't get it.
6 times 3, but I want it as power of 6, so it's 6 to the power of 3, right? So all you do is sit there, you just go 6 squared, 36. 6 cubed, 216. Good enough, that's what I want, right? Okay, so we take the square root. Square root is a radical. The radical expressed as an exponent of the power of 1/2. We then write 216 as 6 cubed. We then do 6 cubed to the 1/2. What's that equal to? So left side is 6 to the 3x. What do we do when we're
We multiply.
multiply? What do we get? 6 to the
3/2.
3 over 2. Now what do we do?
Get a common base.
We have a common base. So now what do we do?
Take the 6
Take them out.
Take out the 6's, right? 3x is equal to
3/2. Woo.
3 over 2. Then we
What's
solve.
x equal
What's x equal to? Well, multiply both sides by 2. Get 6x is equal to 3. So x is 3 over 6, which is 1/2.
to? Mein Gott.
You want to check that? We don't have to do anything. Well, I mean, if we want to check it, we can go 6 to the 3/2. But we already know that this side, well, maybe we don't. Maybe we made a mistake here, right? So go 6 to the power of 3 times 1/2, hit enter, go square root 216, hit enter. They should be the same. Yep.
Why do you do like 1/2 of 216?
Okay, so it's square root 216.
Yeah.
So square root as an exponent is raising something to the power of 1/2.
Okay.
Okay,
Just have to remember that.
you got to know that.
Okay.
Don't remember it. Know it. It's really just converting radical form to exponential, right? So if I had like 4, the cube root of 4 to the 5th, I would write that as 4 to the 5th, right? Converting radical form to exponential form. Okay, ooh, tricky one. 5. Okay, so what do we do before we do anything else? What should the first step be? What must the first step be? Forget should.
Find the common
We got to divide both sides by 5. So we can't solve for this power 2 to the 3x plus 1 with that 5 there, right? So we need to isolate the power. We need to isolate the 2 to the 3x plus 1. So we'll do that. We'll divide both sides by 5. So 2 to the 3x plus 1 is equal to 64. Okay? 64 we know is the power of 2. Right? I know it's 2 to the 6th. You should be able to come up with it's 2 to the 6th. So we go 2 to the 3x plus 1 is equal to 2 to the 6th. Okay. Now check that. I mean, you know, if you're doing it yourself, you're not really sure. You have an idea that maybe it's 5, maybe it's 6, maybe it's 7. Not sure which. So just try it. 2 to the 5th, 32. All right, so then it's 2 to the 6th, right? I got to go multiply by 2. Okay, what do I write next? So it's
Yeah, if it dropped.
apparently I write nothing next. So if the bases are the same, then the exponents must be the same. So I equate the exponents. Say 3x plus 1 is 6. So what's 3x equal to? 5. And what's x equal to? 5 over 3. Okay, you want to check that? You go 5 times 2 to the power of, put a bracket down, 3 times, put another bracket, 5 divided by 3, put a bracket down, plus 1, close it all off, hit enter, you should see 320. You just put the x into the original expression and say, hey, it's only on the left side, so I'm just going to go 5 times 2. So here's what you'd put into your calculator. You go 5 times 2 to the power of 3 times, okay, what did we say it was? 5/3, so 5 divided by 3 plus 1. Okay, stick that into your calculator, hit enter, should say 320. Wow. It's not a talking calculator, so it actually won't say 320. There actually are some talking calculators, so if it were a talking calculator, it would say 320. Okay, it's not, but the display will show you 320. 9 to the 2x plus 1 is equal to 1 over 243. Okay, so we did one with a radical, right, square root, so we had to say, oh, square root, that's an exponent of a half. We got a 1 over 243, so we can write that as, start this out, we'll just keep that as a 9. 243 to the power of -1. Right? We need to write it in exponential form, right? And it's a 1 over, so it's 243 to the -1. What's a common base between 9 and 243? So we can write 9 and 243 both as powers of, well, what's 9 a power of? 3. And what power of 3 is 9? 3 squared, right? Now, I'm going to write the 2x plus 1 in brackets to remind me when I do power to a power that I will get 4x plus, or sorry, yeah, 4x plus 2, right? Oh, Calgary Flames, straightforward Sven Berchi to...
How do you read all that?
It comes through my watch. It's on here, but I messed it up.
You can read all that on your watch.
Yeah, my daughter won't be happy. She likes Berchi, but it's gone. I think it said to Vancouver. Can we write 243 as a power of 3? Well, use your fingers. So we go 3, 9, 27, 81, 243, right? I don't necessarily expect you to know. I expect you to know that 243 is a power of 3, and then if you got a calculator in front of you, you can figure out which power of 3. So 243 is 3 to the 5th. Okay, so we just replace it. So first we had to take the 1 over 243 and write it as 243 to the -1. Okay, so we change it to from a rational form to an exponential form. Then we write 243 as a power of 3. Now we use power to a power, so the left side becomes what? 3 to the 4x plus 2, and the right side is 3 to the, and the next thing we write is okay, so we have the bases the same, they're both written as 3. We equate the exponents, and x is equal to -7 over 4. You want to check that, you're going to go 9 to the power of 2 times -7 over 4, you know, and hit enter. And then you got to go 1 divided by 243 and hit enter, right? You're going to have to work out both sides. Right? And see if they are the same. Okay, keep going. 2 to the 9x is equal to 8. Okay, what do we got to do? We have to change what to what?
Oh my goodness.
So 8 has to become 2 to the 3, right? 2 cubed. Then what do we say? Now, if the question says rounded to the nearest tenth, then what's x? Zero 0.3. This is rounded to the nearest hundredth, 0.33. Okay, so it could be that it's a numeric response question and you're doing some rounding. Okay, how are you going to solve this one? Can't write 800 as a power of 5. So the only thing we can do is solve this graphically, right? We're going to have to do y1 is equal to 5 to the x minus 1. And y2 is 800. So I'm going to need a calculator. So let's grab a calculator here. I'm going to have to set a window. So let's figure it out, right? I mean, 5 cubed is 625. Or sorry, what do we got? We got 525, 125, 625, and then some number over 3,000. So the x values can go up to about 5 or 6. So x min, well, let's say 0 to 10. Scale of 1. Y min, let's go 0 up to 1,000, right? Because I need to see 1,000, let's go by hundreds. Okay, let's go to y equals. Y1 is 5 to the power of, you need brackets here, x minus 1. And y2 is 800. Okay, so left side I'm graphing as y1, it'll be in blue. Right side I'm graphing as y2, it's in red. I've set my window accordingly. I hit graph, and what do we get? X max less than x min. Okay, I've got something wrong in my window range. Oh, never put a 10 in there, put a 0. Okay, let's graph that. So there's 5 to the x minus 1, right? Every exponential kind of starts out pretty low, right? And then it zooms up. Remember that this is 100 here, so it takes a little while before it reaches 100, but then it's going up pretty quick. Second calc, we got to do an intersect. We're looking for, so I'm just going to move. There we go, close enough. 1, 2, 3. Intersection 5.15. Round to the nearest tenth. Well, x minus 1. Right? Oh no, we graphed 5 to the x minus 1. So it's just x equals 5.15. X is equal to 5.2.
So you just put like y equals the first part and then y2 equals 800.
Yeah, so y1 is the left side of the equation, right? We're trying to find out what makes these guys equal. So we set y1 and y2 to both graph, and then we're looking for the intersection. What value of x? Okay, just take a look at the graph.
Can we do that for everything?
You can do that for a lot of things.
Okay.
So valid strategy, right? I mean, why am I going to solve something algebraically on, now, when I give you a quiz, it's going to say algebraically determine, you got to show me the work. On the actual diploma, they give you something like this, just graph it, right? But usually what they do is they do something so that you can't just graph it, right?
They have
They'll
like a
give-
multiple choice question and just like that.
You get multiple choice just like that. I would actually just plug in each of the values for x until I found the one that works. Which means nobody worth their salt is going to write that multiple choice question. Right? Like, we just don't do it. It's like, what are we testing if we were testing your ability to plug 4 numbers in and get the correct answer? Like, it's not grade 1. So we want there to be some mathematical understanding, which means we usually write something like this so you can't solve it just by plugging it into your calculator, right? It has to be some knowledge. Okay, you want to check this, you just go 5 to, not here, sorry, you quit. So you go 5 to the power of 5.2 minus 1. Now, what do I expect to get out of this when I hit enter? Am I going to see exactly 800? It's going to be, I rounded to the nearest tenth, so I'm not going to see exactly 800, right? I'm going to see something close. Should be ballpark, 862, right? It's rounding to the nearest tenth. You know, it stored the value in x, so we could go 5 to the power of x minus 1, okay? Because it put that value in for x, right? I think. So now if I hit enter, I should see 800. I hadn't tried that before, so I didn't know if it worked. But we told the calculator to solve for x. It did. It stored the value, the 5.15, blah, 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 in x. So when I'm using that exact value for x, we're going to get exactly 800. When I'm using a rounded value, like 5.2, we're not getting 800, right? We're in the ballpark. It's not like it was 8,000 or something. You know, it's close, but. All right. Got a few more. 8 to the 2x plus 1 is equal to 1/2 times 3 to the x plus 1. Okay, I probably should multiply both sides by 2, right? Get rid of the half. It'll kind of simplify what I'm going to do. Now, if I do that, I'm going to get, no, actually, it's not even worth doing, right? Because I don't have an 8 there. I've got an 8 there. I'd have to convert it to a 2. I can't get these bases to be the same. So the only way we can solve this, graphing calculator. All right, so we go to y equals. We're just going to clear out what's in there. Okay, 8 to the power of 2x plus 1, okay, in brackets. Enter. 1/2, 1 divided by 2. There's my half. Times 3 to the power of x plus 1. I'm going to put it in brackets. I don't need to. It would all stay up there, but that's nice. I mean, depending on the calculator, some calculators you do need to. All right, now, I want to get some idea. So let's do this. Let's go into the table and just sort of look and see when are they about equal to each other, right? Because that's what we want, right? We want y1 and y2 to be equal. So just to get an idea. All right, see, this is like huge numbers and that's small. So it's probably like a small negative number, right? All right, so that means we're looking somewhere between like -2 and +1. Right? So I don't want a big window here. So -2. Actually, you know what? Let's just go zoom standard. Let's graph it in the standard window and see what we get. So the blue line, that's 8 to the 2x plus 1. Okay, we got an idea what that looks. We know what 8 to the x looks like. Takes off pretty quick. And the red line, well, here comes the red line. So we're looking about here, right? That's where they cross. Now, there's fancy things you can do on your calculator. You can do zoom box, right? And so what that does, starts out at the origin, and you can just sort of, you know, I want to draw a box. Not this, come on. And I know it's got to include that little bit there. So I'm just going to go up a ways. And I'm going to go over slowly. Good enough. I'm going to hit enter. And now I'm going to draw down and across. Okay? And basically I just want to box in the area that I'm looking at. And that's what I've done, right? Because I know the answer is somewhere around here. I just want to see it a little closer. Okay, so blue line, that's y1, 8 to the 2x plus 1. Red line, it's 1/2 times 3 to the x plus 1. Here it comes. And it's going to cross right about there. So that's what I want to find, right? So I use zoom box to kind of go in on the area and say it's somewhere close to there. Second calc, looking for the intersection, right? First curve, you notice it's down here, so I'm just going to move about to the point of intersection. If I can ever get there. Okay, 1, 2, 3, 3. 0.547, so 0, oh, sorry, negative, watch, there's a little negative in there. So negative 0.5, right? Negative, so x is equal to negative 0.5. Okay? You could check that. Right, we can quit out of this. If I wanted to check this, I know that negative 0.5 is not going to give me the exact same answer because it's almost 0.55, but it's 0.547. So I would just do this, 8 to the power of bracket 2x. Remember, the number is stored in x. So there's 8 to the 2x plus 1, 0.822440781, whatever. And 1/2, so 1/2 times 3 to the power of x plus 1, bracket x plus 1. And what do I expect to see? Exactly the same, right? All the way down to the end. Okay. Now, I'll be somewhat close if I use negative 0.5, but it won't be exact, right? Like, it'll actually be, a little bit far off. But rounded to the nearest tenth, that is your answer. Okay, applications. Applications. Here we go. Applications. A lot of applications of exponential functions in finance, because in finance you get exponential growth, right? If you have a compound interest savings account, you don't get much these days, but that's an example of an exponential function. If you take the value of a piece of art appreciating over time, that would be an exponential function. A rare car would increase as an exponential function. And you can get an equation like this, or a function. So a of t is equal to a sub 0. So we call that a naught, right? British word for zero, naught, N-O-G-H-T. So you could say a sub 0 or a naught times b to the t. So a naught, a sub 0, is the initial amount. Okay, so we could be talking bacterial growth. It would be the initial number of bacteria you had. Could be the value of a painting. It would be the initial value of a painting, or the initial value of a car, something that could potentially go up in value. And a of t is the amount at the end of t time periods, right? So t time periods. So if it's bacterial growth, it could be after t minutes. If it's value of a painting, it could be after t years, right? So it's the amount after a certain period of time, and the time's got to be in a certain number of units. Okay, so let's do a problem that, so the value of a painting increases at 4% per year. The value of the painting after t years can be represented by the exponential function is equal to V naught 1.04 to the power of t. So in this case, V naught, or V sub 0, would be the initial value of the painting. V would be the final value of the painting after some amount of time t, which is in years. Okay, since the b value, remember this is b, right? The base of the exponential function is b. Since it's greater than 1, what's going on here? Growth or decay? Growth, right? And considering it's increasing at 4% per year, it has to be growth, right? So we know the base of the exponential function has to be bigger than 1. That's what gives us growth. Between 0 and 1 is decay, right? That could be like the half-life of a radioactive substance or something along those lines. Okay, so we got this equation, right? V is V sub 0 or V naught 1.04 to the t. So here's a question. If the current value of the painting is $50,000, state an exponential function, actually state the exponential function for the value after t years. So the big question is, what's the 50,000 of, you got three things there, right? V, V naught, and T. Which one is 50,000? V naught, right? It's the initial amount. What's it worth initially? Okay. So the equation is the value is equal to 50,000 times 1.04 to the T. Okay. So that's the exponential function we're going to use. B, calculate the value after 10 years. Okay, what are we going to do to get the value after 10 years? Yeah, so we're going to say, well, I've got my expression for value, right? And we want 10 years, and t is the number of years. So V is equal to 50,000, 1.04 to the 10. So what's that? So we're going to get our calculator. Okay, what do you got? Give it to me. To the nearest dollar. How many dollars? 70, so 74012. Like so. Okay. There's no point going to the nearest penny, right? I mean, it's like, whatever. How long will it take the painting to at least double in value? So part C. How many years comma, to the nearest year will it take for the painting to at least double in value? So what are we going to put into the formula? V equals 50,000, 1.04 to the t. So what's the big V on the left? What do we want it to be worth? 100,000, right? We want it to double in value. So we're going to say 100,000 is equal to 50,000 times 1.04 to the t. So we want to know what's t when it's worth $100,000, right? Like how many years will it take? And we want that to the nearest year. So how are we going to solve this? We're going to plug it into our calculator, right? Actually, before we do that, we can simplify this equation. What can we do to make it simpler? Yeah, divide both sides by 50,000, right? I mean, why put in, otherwise you got to put in a 50,000, 100,000. Your window has to be big enough to show 100,000. Divide both sides by 50,000. And you got 2 is equal to 1.04 to the t. I could do that in a regular window, right? I just want to see 2. Okay, let's go back here. Go to y equals, actually, yeah, okay. So clear out what's in here. So I've got 1.04 to the power of, okay, we can't use t, so we'll use x. And we want the y value to be 2, right? I want to know when is this 2. I'm just going to hit zoom standard, go back to the standard window, okay? Because I know I'll see 2 along here somewhere, right? Blue line is 1.04 to the t. And then the red line will be 2. And I could see that we're not quite there. Okay. So let's go back to the window. So okay, I don't need any x values that are less than 0, right? Apparently I need to go a little bit further out. So let's go out as far as maybe 20 by 1. My y values, well, 0 to 3 is good enough, right? Because I just need to see 2. So we'll graph that. So here's 1.04 to the power of t, and this will be 2, right? Will be along here. And we want this. Okay. Now, if 20 wasn't enough, then I'd extend it out a bit more, right? Sometimes you gotta play with the numbers and just try it until you get something that works. So second calc, intersect. Just gonna move to the point of intersection in under 3 seconds at a time. Okay, hit enter 3 times. I guess 17.67. So what's the answer? 18. What if it were 17.4? What would the answer be? Still 18. What if it was 17.2? Still 18. So here's the key wording here, right? So we can see from here it takes 17.7 years, right? Life is good. It's just going to round to 18. Normal rounding is going to do that for us anyways. Whoops. What did we do? Must have gone a page ahead. Okay, so t is equal to 17.67, so it will take 18 years. So there's some key words in here. The painting to at least double. So we know it's going to take 17.67 years. That's 17 and about 2/3 of a year. 2/3 of a year is like 8 months. So in August of some year, it's going to be worth 100,000. Okay, but we need to know 2 things. That it at least doubles. Not that it doubles, but it at least doubles. Because when we take that out to the nearest year, no matter what this is, if it's 17.2, we have to keep going, right? Because we'll still be underneath, right? We won't have hit the doubled in value yet. So anywhere along here, you haven't yet hit double in value. At 18 years, you're actually more than double in value, right? But we need to at least double. So it's got to be worth at least 100,000. So we have to take this and go up to the nearest whole year. Even if it were 17.2 years, we would still have to go up to the next highest year. Because if we go down, if we use normal rounding, if it was 17.2, we use normal rounding, our value is going to be down here somewhere, right? It will not have hit double just yet. Okay, so when we say nearest year and at least double, and that's kind of wording that you should see on the exam, right? Although they should use rounding like this, where it's unambiguous, right? If we want 18 as an answer, we'll make sure the answer comes out over 17 and a half, so you will just normally round to 18, right? We're not there to fool you on rounding. Okay, but on a quiz, I might be, because you're just going to have to remember, hey, it's 17.2, but we got to go to 18, right? To at least double in value. All right, last example. Half-life. Half-life. So half-life is associated with radioactive substances. You can get an equation like this. The amount after time t is the initial amount. Now the base, not 2, because that's doubling, it's going to be 1/2, because it's halving, right? It's having. Only don't want to confuse having with having, the one that has the L and the one that doesn't have the L but are pronounced the same.
Kyla Starlight to the main office, please. Kyla Starlight.
So in this case, there's a little extra thing introduced here, right? Which is this H. So then we need to explain to you. So if you're given an equation like this, it'll be in a little box at the top, right? So here's this equation, and then it'll tell you what each of the things is, right? So they'll say A naught is the initial amount. So anytime a formula that's not on your formula sheet is given to you, then there'll be an explanation of what's in this formula, right? So A naught is the initial amount. A of t is the final amount after time t. H, well, t is the amount of time. And H is the half-life of the substance. So in other words, it's how long it takes for there to be, you know how radioactive decay works, right? You got like a pile of radioactive stuff, and in its half-life, so if its half-life is 1,000 years, then in 1,000 years you'll have half the amount of radioactivity. In another 1,000 years you'll have half of that again, another 1,000, half of that again, and so on. These two guys here, okay, they need to be in the same units. Okay, so both in years, both in months, both in days, both in minutes, both in hours, whatever. If they're not in the same units, then you need to convert them to the same units, right? So if one is given in days and the other one's given in hours, convert them both into hours. Okay, that shouldn't happen. They tossed that one question off of a diploma where they gave you different time units, and so they're not going to make that mistake again, right? It just, you know, if you're not reading it carefully, you're just not going to get it right. T over H, this thing here works out to be the number of half-lives. Okay, so T is the amount of time. So imagine we've got a substance with a half-life of 1 day, and we're doing this for 1 week. 1 week is 7 days, so the 7 divided by 1 will give you 7 half-lives, right? Every day for a week, it's going to go through a half-life. If the half-life is 30 minutes and the time is 5 hours, I guess, okay, 30 minutes is half an hour, right? So we'll have 5 divided by 2. We'll go through 5 we'll go through 2.5 half-lives, right? So each time. So T over H is just the number of half-lives. Okay, let's do a question that uses this. Radioactive iodine. Radioactive iodine. Okay, so we know the thyroid gland uses iodine, right? So if doctors want to check and say, is this thing working normally or is there a problem, then they can inject you with some radioactive iodine. Right? Sounds like a good thing to do. And they can measure the rate of uptake of a healthy thyroid gland. They know how much iodine in a healthy thyroid would, previously healthy thyroid gland before you put radioactive iodine. Right? It's okay. They use a form that won't damage you too much. Okay, so a healthy thyroid will absorb the radioactivity according to the model over 8.1. Okay, so 100 times 1/2 to the power of t over 8.1. Okay, where a of t is the amount so we're giving you this formula, right? Then there's going to be a box at the top of the question with all of this in it. It's called the context, right? So what's going on here? So here's what's going on here, right? This is what's happening. So where A of t is the percentage of radioactivity, in the blood after t days. So what they do is they give you this capsule of radioactive iodine to swallow, and then they measure the amount of radioactivity in your blood after 6 hours and after 24 hours. Okay, and they use a gamma probe. So they just stick a probe up against you. See,
They'll probe.
yeah, they turn off the lights and see if you're glowing in the dark or no. So they're just using a gamma probe. Okay, so more context, right? So a pill is given to swallow. And the amount of radioactivity is measured after 6 hours and 24 hours. And they have experimented on college students who they pay money to, right? So if your university is always says, hey, you want to make 25 bucks? Just allow us to experiment upon you. So you might want to see what it is. Like, I'll take some psych test for 25 bucks, but you're not injecting me with radioactive. Although, if I could get the powers. So you have to decide if it's worth the money, right? So they take supposedly normal people and they check this, right? And they say, okay, after 6, and they come up with a range of values, and that's what they're going to check against. All right, so there you go. That's the context, right? It's all in one big box. Then we get the actual question. So now a question, right? Using the model, determine a word you will never see on the diploma, because determine means show your work, but it will be on a quiz, right? So show your work. Determine to the nearest whole number the percentage of radioactive iodine in the blood of a healthy patient after 6 hours, and after 24 hours. Okay, so we've got a model. We're just plugging in. We're saying this is a model for a healthy patient. We want to get some numbers to know what a healthy patient would have, and then we can compare somebody else's test to that of a healthy patient. There's one other thing you need to know, which is not here. This 8.1 is in days. So we're saying that the half-life of this radioactive iodine they're giving you is 8.1 days. Okay, so that's important. All right, we got a formula. We want the amount after 6 hours. But 6 hours is 0.25 of a day, right? Because we have to have the same units. So if we use 6 here, then we have to go 24 times 8.1 for the half-life, right? It's got to be in the same unit. So 6 hours is 1/4 of a day, right? 6 hours is 6 over 24 is 0.25 days. So 100, that's just the percent, right? They give you got 100% of this radioactivity in you, times 1/2 to the 0.25 divided by 8.1. Okay, just a calculator thing here, right? Takes like 10 minutes to read this, figure out what's going on, and then just say, but I just got to plug this into my calculator. So why this exam takes longer than the 30-1 exam, right? You got all these contexts you got to read and stuff. And theirs is just, here's some math. Here's some more math. Do more math. You got to wade through the words. Okay, so all we do is go in our calculator, type in 100 times 1/2 to the power of 0.25 divided by 8.1. All right, turn this thing back on. Get out of the graph. 100. Bracket 1 divided by 2 bracket to the power of bracket, I need another bracket, 0.25 divided by 8.1, close bracket, enter. 97.9, 97.9, that's to the nearest 10th, right? So 97.9. So after 6 hours, they still expect to see 97.9% of the radioactivity. After 24 hours, so that's 1 day, right? 1 day, you're going to put a 1 in there. It's 100 times 1/2 to the 1 over 8.1. So all I got to do is take this thing that I already have and change that 0.25 to 1.0 and hit enter. 91.8%. Okay, 91, whoops.
Oh,
Okay, just kicked it forward a page. So this is 91.8%. And now the real question, because this was really just, you know, this was
a question.
yeah, no, this is just busy work, right? It's like, really, we're going to give you marks for plugging numbers into this thing? No, of course not,
you
right?
should.
Yeah, you'd think, right? It's got to be worth something. So here's the real question. A patient missed the 24-hour appointment. And when the doctor finally took the measurement, he determined the patient had a healthy thyroid. Period. When the doctor took the measurement, she, what do you want? She determined the patient had a healthy thyroid. if the percentage of radioactive iodine was measured at 84.3%. Then how many hours had elapsed? Period. I mean, question mark. One of these long classes. So tomorrow we'll just do a work period on this, and then Wednesday we can test everything, right? It's only fair you've had to sit here through all of this, so I can reward you with at least at least a class on which to work on this stuff.
Wait, what does that last thing say?
So if we ended up with 84.3%, so yeah.
What's buzzwordy? Oh, I see.
Elapsed. All right, so we've got an equation, right? A of t is equal to A naught times 1/2 to the t over h. We know that we will end up with 84.3%. We know we started with 100%. We know that the half-life is 8.1 days. What we don't know is what's t. At this point, the only way we can solve that, first off, let's get rid of the 100, right? So we're going to divide both sides by 100. So if we graph this as y1 and this as y2, we'll get t, right? So that's what we're going to do. We're going to go to y equals. We're going to clear out everything that's in here. So I want 0.843 with the 8 in front. 0.843. And I've got 1/2, so 1 divided by 2, to the power of x divided by 8.1. And I'm just going to go zoom standard. So there's the 0.843, right? It's just around 1. And here comes this, it's a decay function, right? The base is between 0 and 1. That's decay. Somewhere in here is where it's going on. So I might want to just reset my window. Okay, I'm going to go 0 to 10 seemed reasonable by ones. And let's go like -1 to 1 and regraph this. So the 0.843 is up pretty high, pretty close to the top. And here's our line coming through, right? A lot easier to just kind of see that. Okay, second calc, intersect. Goes, just move along. One, 2, 3, the x value. 1.9958, so let's call it 2.0. Right, we got 1.9958, so t. Okay, what unit of time is t measured in? Days. So how many hours was it? Okay, so the patient missed. That was lousy weather, couldn't get in town, had to come the next day at whatever time. 48 hours had elapsed. 84.3% was measured. That works out to be a normal amount, right? The expected amount.